All right, we are looking at chapter 3, exploring two variable quantitative data, specifically looking at section 3.1, a scatter plot and correlation. So, some learning targets for us today. By the end of this section, you should be able to distinguish between exploratory and response variables for qualitative data, quantitative data. Make a scatter plot to display the relationship between two qual- quantitative variables, describe the direction, form, and strength of a relationship displayed in a scatter plot, and identify unusual features, interpret the correlation, understand the basic properties of correlation, including how the correlation is influenced by unusual points, and distinguish correlation from causation. So, some of this might be a review since we teach this after you've already looked at chapter 4 and 5. So, just hang with me. It's a nice review for us here. So one variable data set is sometimes called univariate data. So it's uni for one variable. And then a data set that describes the relationship between two variables is sometimes called bivariate. So two as in that bi there. Analysis of relationships between two variables built on the same tools we use to analyze one variable. So we're going to plot the data, then look for an overall pattern. We're going to have numerical summaries. And then when there's a regular overall pattern, use a simplified model to describe it. So a lot of the things that we did in chapter 1 and 2 with one variable data, we're going to look at two variable data here. So one of the big things is to distinguish the difference between exploratory and response variables. We saw this a little bit already in first semester, but it's good to see it and to reacquaint yourselves with it because those are the vocab words that AP Stats uses, and it's the vocab words that you need to use. So most statistical studies examine data on more than one variable, and the analysis of the relationship between those two variables builds on the same tools we talked about from one variable. So response variable measures the outcome of a study, and then the exploratory variable may help predict or explain changes in the response variable. Now down here, I added these two things just so you have it to help remind yourself, but you should not use these words, okay? We should always use response variable and exploratory variable. You should not use dependent independent. Um, in stats, we use the response variable and the exploratory. So I'm writing this just one time for you to recall and remember and kind of help you here, but then we're going to use response and exploratory. So the response variable is always on the x-axis. It is the dependent variable, and it's what the outcomes is, right? It responds to something, is kind of how I think about it. The exploratory variable is always on the x-axis, and it's the independent. You're exploring if this thing will affect something, right? You're exploring what happens if I do something to here. So it's the independent variable. This is kind of a big note, especially the bottom part, and you should all know this since we've looked at unit or chapter 4 already, but correlation or a relationship does not mean causation. All right, remember we can only claim a cause and effect relationship if it is a good experiment. All right, so there could be a relationship, but there could not. It doesn't guarantee that there's causation being at play. So scatter plots. A scatter plot shows the relationship or the association between two quantitative variables measured on the same individual. The values of one variable appear on the horizontal axis, and the values on the other variable appear on the vertical axis. Each individual in the dataset appears as a point in the graph. We should be pretty familiar with um, scatter plots. If you wanted to kind of see one on your calculator, let's see if I can pull this up here. Just for you, this is not going to be the best data just because it's kind of here. But if you went into second stat plot, turn it on, um, this first data set, that first number is a scatter plot. So you can see it there, and then you're going to want L1. Let's say our L1 was um, our exploratory, and our L2 was our response variable. I'm going to zoom in. I'm going to go zoom stat. And now this is not going to be a very good scatter plot, but press enter, and you can kind of see my exploratory is on the bottom, my response is on the Y, and each point is one of the data points that I have. Right. So when you make a scatter plot, a couple of things. One, you must label the axes, right? And so here's another kind of way to help you remember. The exploratory variable is always on the x-axis, right? X and x-axis. The response variable goes on the vertical axis. If there's no exploratory variable, either variable can go on the horizontal. Scale the axes, plot the individual data points, and I'm going to take it one step further and create a label for the graph. Okay, what are you actually looking at? Now, to describe the scatter plots, we're going to follow a little basic strategy here. The first thing is going to be if there is an actual association. Basically, is there a relationship? It's either positive, negative, or neither. I don't love these definitions. I think you can understand a positive association essentially has a positive slope. A negative association would have essentially a negative slope. And then no association would be there's not really a positive or a negative. It's just kind of data's all over the place. That's how I think about it. I think these definitions are a little clunky, so I'm not going to kind of require you to remember them. But it's the idea that the positive association is that kind of as you increase in the x, the increase in the y as well, and vice versa. So here, this one on my calculator would be a positive association. We have some others here. Oh, I guess I'll give you a second to time of guess what you think each one of these are, and then go. So this first one's a positive association for the most part. It is going kind of up and to the right. The second one definitely is a negative association. And then down here at the bottom, this is going to be no association. It's just kind of data all over the place. So how do you describe a scatter plot? We had things to describe one variable data. We had that SOCS, SOCS, shape, outlier, center, spread. For a scatter plot, we have a similar four-part process. The first is the direction, which we just talked about. Is it positive association, negative association, or no association at all? The second is the form. So a scatter plot can show a linear form or a nonlinear form. So it's just the overall pattern. Does it seem to be a linear situation or non? Second is the strength. The strength is how strong or weak the association is. And we'll talk about more like how to actually quantify it numerically. But I think this is a pretty good understanding. An association is strong if the points don't deviate much from the identified. Essentially, if you were to kind of draw, if this was linear and you were to draw in a line, do those points vary a lot from that line, or are they pretty close to it? The closer they are to forming that line, the stronger the relationship is going to be, and the stronger the strength. And then lastly, is there any unusual features? So we'll take a look at what that might include here in a second. This is a good caution they put in. When describing the associations shown in a scatter plot, write in the context of the problem. So you want to write about both variables and describe kind of how they are behaving with each other. Specifically as like if it's a negative, which one is decreasing which, and vice versa. So we'll take a look at what that means. Here's some data here and a scatter plot. And so let's kind of go through the process. I'm going to say there is a moderately strong negative curved relationship now between the percent of students in the state who take the SAT and the mean SAT math score. So you see how they give us both variables? And it says, furthermore, there are two distinct clusters of states and two unusual points that fall outside the overall pattern. So let's take a look at, do we hit all four? first thing, the strength, a moderately strong. So we got the strength in there. You'll always have either it's a weak, weak, moderately strong, strong, or those are kind of the basis. Or you could say no relationship for strength. The direction tells us positive. Oh, I guess the direction is a positive, negative, or none. And then the form is if it's curved or linear or what kind of shape it is. And then the last is the unusual feature. So you can kind of see here, this is one kind of big group. Here's another group. And I would say probably these 2 points are kind of outlying out of it. So just giving us a little bit more context, a little bit more description of what this graph actually looks like, what the scatter plot looks like. So we said we talk about how do you know if it's like strong, weak, moderately strong, and kind of what the cutoff is for each of those. So when the association between two quantitative variables is linear, we can use the word correlation. So it must be linear. Okay, that's the big thing, it must be linear. We can use the correlation or the R value to help describe the strength and direction. So the correlation R measures the direction and strength of the association. And again, it must be linear. So if it's a linear association, then you can use correlation R value, okay? Another caution, because it's super important, it has to be linear first. Okay? So some important properties of correlation for R. R is always a number between -1 and 1, inclusive. The correlation R indicates the direction of the linear relationship by the sign. So positive. So if R is bigger than 0, it's positive. If R is less than 0, it's a negative association. -1 and 1 only occur for a perfectly straight linear relationship, and all the points must line up exactly on the straight line. As the linear relationship is strong, the correlation will be closer to 0 or 1 and -1. And if the relationship is weak, the correlation will be close to 0. So here's 6 scatter plots with the different correlations. You can see this is 0. There's really no correlation here. -0.3, still, that's very, very weak for 0.3. R is 0.5. Okay, that's somewhat of a positive relationship. And in the bottom, we're starting to get a little bit stronger. -0.7, and then +0.9, and -0.99. So you can see the larger the correlation is, or the farther it is from 0, the closer and closer these get to forming an actual line. So, and like we said, in order to be perfect 1, every data point would have to fall directly on this line. So, some extra cautions, and you should know this. All right, but correlation does not mean causation. You've probably heard this 1,000 times, but today's 1,005. So correlation does not mean causation. Correlation does not tell us the form. It does not tell us if something's linear or not. Remember, you can only use correlation if you already know it's linear. If you don't know it's linear, the correlation doesn't make sense to be used. And like I said, it should only be used for linear relationships. So you must know it's linear, and then you can use correlation. If you don't know it, you don't know anything about the form. All right, and then this is big. Correlation is not a resistant measure of strength. So what that means is that it's going to get pulled based on those extreme values. So really large and very small x values will have a lot of impact on that correlation. It's just like how mean is not resistant, right? It gets swayed by large data points. So same thing with the correlation. Okay, how to calculate correlation. Suppose that we have a data on variables x and y for n individuals. The values for the first individual are x1 and y1. The values of the second individual are x2 and y2, and so on. The means and standard deviation for the two variables are x bar and sx, and then y bar and sy. The correlation is this big messy formula. 1 divided by n minus 1 times the x value minus the x bar divided by s of x times y1 minus y bar over s of y. And then you add every single point. Now, the kind of cool thing here is x1 minus x bar divided by s of x. That's like a z-score for x. And y1 minus y bar over s of y. That's like a z-score for this y. And we know that z-scores are unitless. So if I have like the essentially the same thing of a unitless measure times another unitless measure, this is going to be unitless. So r is actually also unitless. This is a big point. We don't really care too much about the formula because the calculator can do it for us, but we do care about being able to interpret and understand what it is and some important facts. So correlation requires that both variables be quantitative. That makes sense. You really wouldn't do a scatter plot if they weren't already quantitative. Correlation makes no distinction between exploratory and response variables. It doesn't tell you one or the other. R does not change when we change the units of measurement of x, y, or both. And that's because the correlation, like I said, of R has no unit measure. It's just a number. So regardless of how you scale these values or whatnot, the relationship's going to be the same as long as you scale them the same. But it doesn't matter what the unit is on them. It doesn't matter if you had centimeters and then you went to millimeters or whatever the unit was. It's going to have the same correlation because it has the same R value or because it is unitless. So the changing the units won't change the correlation. All right. And that is all for 3.1. So to finish up the learning targets, you should be able to distinguish the exploratory and response variables for quantitative data. Remember, the exploratory is the x-axis one. It is also the independent. The response variable is the y-axis or the dependent variable, the response to something. Making a scatter plot to describe the relationship between two quantitative variables. When you describe the direction, so positive, negative, or none. Form, is it linear or nonlinear? The strength, how strong of that value is, looking at the R value. And any unusual features. These are all three things you need to put in your describe. You interpret the correlation. Understand the basic properties of correlation, including how the correlation is influenced by unusual points. Remember, it is not resistant. So very large values have the potential to influence the correlation quite a bit. And then understand that correlation does not mean causation. All right, and that's all we have for 3.1.